Okay, so we move on to binomial model valuation of options. So this is a discrete time approach to valuing options. Later we're going to do the continuous time approach. The difference between the two is, in some sense, a philosophical one, in that do you know stock prices on a continuous basis, continuous time basis, or do you know it on a discrete time basis? The continuous time lends itself more to closed formulas for the types of simple options that you can value using continuous time approach. The discrete time approach is more flexible in that it will allow you to value options pretty much irrespective of what their payoffs are. It's a lot more open-handed than the continuous time approach. The difference being, though, that you don't get explicit closed formulas at the end of the day. You get an algorithm or a process by which you can evaluate the values of the options. As the time steps in the discrete process go to 0, you can show theoretically that the results go from the discrete time to the continuous time, at least for the simple European options. But we're not going to do that here. We're going to just focus on that as a convenient, very useful way of valuing options. It also allows us to introduce various important topics. So, for example, the idea of a replicating portfolio. So for the first time, it's going to allow me to justify to you that if I write an option, if I'm careful about the way I invest the premium that you give to me, I can in fact actually cover all my assets as the writer. And therefore, there's a proper strategy to follow. And it's not surprising that the actual way that we come to value that option at the end of the day depends on the replicating portfolio, which is in a sense the strategy that I have to carry out as the writer of the option at each stage in the process, at time step. So the way that it works is the following. We're going to suppose that we've got an asset, an underlying asset that's got a price of ST at time t. That price itself, we're going to assume behaves in a certain way. The way that it behaves is at time t plus t, as you go from time t to t plus delta t, it will jump up to either UST or DST, where U and D are numbers that you multiply that ST, the original ST value at the time t, to give you the up or the down. So this is a binomial tree. I could have a trinomial tree, so I could have 3 possible outcomes, or I could, if you like, have a quadrinomial tree, but the simplest case is a binomial tree. After one further time step, in the simplest case, we can actually go to the U time step can either go up again to U squared ST, or it can drop to UD times ST, or the D can go down again to D squared ST, or up to UDST, and so on and so forth. So that the actual tree you get is that picture that you get here. And so this is after one time step, you're either UST or DST, U squared, UD or D squared, U cubed, U squared D, UD squared or D cubed. And you can see that in terms of, because U and D are just ordinary numbers, whether you go up and then down, or down and then up, you end up here with the same value of the share, or the underlying asset, sorry. That's not always going to be the case when we come to looking at what the value of the options are. You don't always reconnect. We'll worry about that in a minute. And then you can propagate all the way through and put in as many time steps as you need in order to get between 0 and expiry, the time of the option that you're interested in on that particular underlying asset. Now, what are the values of U and D? Well, we'll worry about that in a minute. The idea is that in the limit as delta t goes to 0, the points on the at that particular time step, it should then basically tend towards the log normal distribution for the asset prices. So the idea is, if you fix the U and the D values, at the end of the day, you'll see later on, you can try and fix them so that the distribution, although these are obviously just samples of that distribution because they're discrete values of the discrete points. We're not looking at a complete. If we're looking at ST, it's not the probability of ST is not doing something like that. We are looking at points that do this. We're taking samples of those points from that distribution. The other thing that you could introduce is the fact that U and D are not the same at different time steps. So at different time steps, you can have different U's and different D's. Okay, that's a more general case, and we'll mention that later on. The first thing that you have to be mindful of is that U and D, there are no arbitrage arguments on U and D. And the idea is that if you don't, so U has to be greater than e to the r delta t. So e to the r delta t is the interest that you would get by putting 1 unit of currency in the bank for an amount delta t time. Okay, in continuous time, or in that step between here and here, if you smooth this out and make it continuous. So U has got to be greater than e to the r delta t, it's got to be greater than d. And the reason for that is that if there's a no arbitrage, you assume no arbitrage. Okay, and then you can look at if U is greater than D is greater than e to the r delta t, by definition, U is greater than D. Okay, that's the one thing you can assume, that U by definition is the larger of the two numbers. If you have U greater than D greater than e to the r delta t, then you could borrow cash, okay, invest in the risky asset, okay, and then even if outcome is ST goes to DST, okay, then you get a guaranteed profit. Why? Well, because if you earn D times ST and you borrowed ST in the first place, you've got to pay ST e to the r delta t back again to the bank. But DST is greater than e to the r DST. So borrow cash ST, and the debt is that you've got to pay back. Okay, it's going to be less than what you can earn. And of course you've got UST there as well. So the first case is that there's an arbitrage here. Okay. And then you've got the other case, which is not brilliantly explained in the notes. When you have that scenario, again U is greater than D, so you get that inequality for free, but it's where e to the r delta t is greater than that. Well, the argument here is you short sell the shares at T, invest ST in the bank, okay, and then at T plus delta T, comma, ST has risen to ST e to the r delta T, so you can see that ST e to the r delta T is greater than U greater than DST. So the point is that this is your money that you've got in the bank, and this is the cost of repaying the short sold asset. Okay, so if it's gone up to UST, you'd have to buy a UST, the share for UST in the market and flog it, but you've got more than enough money to do that. Likewise, if it was DST, if the price of the asset was D times ST, you buy that in the market, but you've got more than the money to do that. So the point is, provided you've got guaranteed profit, which implies arbitrage. So that violates no arbitrage. So the only other option is that you get this. The only other case that you can have is this. So your up value for your share must be greater than e to the r delta t, which must be greater than d, the down value factor for the share. Okay, so this is an example of a recombining binary tree, because after 2 steps, every second step, the nodes come back together. They go apart and then they can come back, or they can follow on other ones, but essentially they recombine. That's different from a non-recombining tree, which we'll look at later on. A non-recombining tree would certainly be the case if you began to worry about different values of u and d, depending on where you were coming from previously, if you had different values of u and d at each stage. Okay, so with that in hand, we can now move on to the idea of replicating the value of the option that we wish to price at each point in time, and we're going to do that using a replicating portfolio. The underlying asset price that the option is going to be based on will follow that binomial tree. What we now have to do is, for each time step and for each possible node, we now have to provide a value for the option. Okay? So if we want to follow the time history of a particular path of a share price, then we would need to know what the value of the option is there. So you see, you could have a share price with probability p, it rises up, and then maybe it comes down with probability 1 minus p, then it goes down again, or it goes up. So all these possible paths, all ways of reaching a particular node here, would be possible histories, time histories of that share price. We're at the moment going to have a real-world probability of p that the share price goes up, and a real-world probability of 1 minus p that the share price goes down. Of course, if you have a trinomial model, you'd have 3 different probabilities here that have to add up to 1, and a quadruple node model, you'd have 4 probabilities that would add up to 1. So the simplest case is where it's binomial. What that p and that 1 minus p is then you would look at what the prices were doing in history, and you would fix it so that you work it out so that you would be able to replicate with these up and down values the price distribution of the log normal. That p and 1 minus p is the same for each time step in the simplest case. For more complicated binomial models, you could have different values of probabilities at each time step. Okay? But we're not going to worry about that. We're just going to stick with the simplest one first of all. We'll worry about that later on. I stress that's a real-world probability. Later on you'll see how things get a bit crazy. Right, so the replicating portfolio is, given that binomial tree, I want to try and find a portfolio of assets that somehow magically equal the value of the option on the underlying asset. Okay? So, a replicating portfolio is a portfolio which at each instant of time consists of the underlying assets with price ST and cash, which is going to be written, it could be bonds, but it could just be cash in the bank. The bonds have a value curly BT, don't confuse that with Brownian motion BT, okay? I'm going to have it as a curly BT, not a capital BT, so that they've got the same expected value of the particular derivative product at the time t plus delta t. So a replicating portfolio is the portfolio I, as the writer, have to have at each moment in time, however I've got to this particular share price at this moment in time, so that the value of that portfolio, if I have to liquidate it, would then give me an equivalent value of the option, so that I could go out and then pay you, if you needed a payoff at that point, that payoff, and I would be covered. So that's really the strategy that we want to do. So it's a combination of the assets and cash or bonds that basically means that at each moment in time, I can actually give you the value of the option if you can exercise it at that particular time. Right. So, notation is we're going to have phi I'm going to have the value of that portfolio, I'm going to have phi units. Well, I can represent it as phi and psi. Phi units is the number of units of underlying asset. So if the underlying asset at time t, okay, has the value st, which it will do, okay, by definition, then the value of the portfolio is the number of underlying assets times the value of the assets, each of those assets, st. And then I'm going to have psi units of this curly b sub t. So that's the bonds or cash. Now if it's just cash, curly b you can just think of as $1 or £1 or whatever unit you're dealing in. Okay? Right. So that is going to be the value that I'm going to hold at this moment in time t. Okay, my replicating portfolio. When I go to time t plus delta t, okay, I'm going to have the value of my portfolio at time t plus delta t. If it moves to the up state, so if the share price rises, it's going to be phi, not times st, but now times u times st, because my share price has risen to u times st. Okay, up there. Then what's happened with my bonds, I've got psi units of those bonds, whatever their face value is, and what happens to bonds? Bonds increase, like cash, like e to the r delta t. So that goes to e to the r delta t. So the point is st goes to ust at that point, and the bonds go to bonds times e to the r delta t. That's just the risk-free rate at which they're growing with interest. Okay? So, that's if I go to the up state. What happens if I go to the down state, and let me call this VU, and unfortunately VD, for down. This is then phi times, well, what's the share price there? It's D times ST. D times ST. What's the bond done? It's psi bond e to the r delta t. So these are exactly the same. These are not. Those terms are not. Like that, okay? So the bonds just drift up anyway, or the cash in the bank will just drift up, or if that's a debt, if this was negative, if psi is negative, it means I borrowed the money, so the debt will just increase, like e to the r delta t. The share price is the thing that changes, it either rises to UST or DST, which then changes the values of the up and the down. Okay. And of course, we've got that U greater than e to the r delta t is greater than d. That's the thing that we have at a priori. And this has got a probability, of course, p, and that's got a probability of 1 minus p, because there's a probability p and a probability 1 minus p that your share has risen or gone down. Okay. So we're up to this point here now. Okay, everybody happy at that stage? Yeah? Right. Now, here's the tricky bit. Okay? So, what have I got here? I started off with something that I know. At time t, I chose a certain shares. I know the share price at time t, and I bought so many bonds. Okay? The thing is, I can say, well, whatever I choose for phi and psi here, I can, given the u and the delta t and the r, I can predict what the future values of those options are going to be. Okay? If I know what phi and psi is, that will lock in the future values of those bonds. So, if I now turn the situation the other way around, I can say, well, let's suppose that time step in the future, I want to be able to specify the value of VU and the value of VD. So that whatever happens in the future, whether the share goes up or the share goes down, I will always have a portfolio that will cover the value that I might have to pay out here, or the value that I might have to pay out there. Okay? So, if VU, VD are fixed, ST and U were fixed by the original binomial tree for the option, for the underlying asset, e to the r delta t is fixed by the market. That r is what the risk-free rate in the market is. B is the bond value. Okay, we'll assume it's 1 if it's cash. So the unknowns here are phi and psi. So I can now do the crazy thing, is I can go back to the future, if you like, specify what my future values I want to get. Given the other parameters, that will tell me how many shares and how many bonds or amount of cash I've got to hold, so that at time t, whatever happens, I will have covered my outgoings. So that's the crazy thing. So we treat VU, VD, UD and ST as things that are known, as well as R. And so we have two equations here for two unknowns, which are phi and psi. So if I solve them for phi and psi, this would tell me that if I want my future values of my portfolio, my replicated portfolio to be VU or VD, and I know that the share price is going to jump to UST or DST, then I'm going to have to buy phi units of those shares at time t to have a chance of getting them. It also tells me that then, substituting it back in, that knowing what VU and U and ST and B and e to the r delta t is, and now what phi is, that's the amount of cash I should have. So that's either cash I borrow or cash I invest into that portfolio in order to have that future value. Now, here's the crazy thing. Okay? Right. If I take those phi and psi values as read, I rewrite this one. I can write it in a more symmetric form here by substituting in the phi value. So purely in terms of just the U, the D, the ST. If I do those and I substitute that back into my expression for VT, what do I get? Well, here was my phi times ST. Phi is this divided by ST, so when I multiply it, that's my phi. My psi is this, okay, times the bond value here. That kills off that bond value there. So that's another reason why we don't really need to know what VT is, but it's there. And then I've got this complicated expression here, which if I pull e to the minus r delta t out the front and play around a little bit and write everything in terms of VU and VD, what do I get? I get this horrible expression, VU, plus 1 minus this horrible expression, VD. This expression is that expression. So if I call that expression Q, I've got e to the minus r delta t, Q VU plus 1 minus Q VD. Now, what does that mean? So VU and VD are the future specified values that I'm interested in. Those are the values that I want at time step t to t plus delta t. Okay? What I've got is Vt is e to the minus r delta t. That's like a discounting value when I discount from t plus delta t back to t. So if you like, it's the amount of money I'd have to invest in order to get a certain amount at t plus delta t. So this is a discounting. Right, and it's into Q, VU, plus 1 minus Q, VD. Where Q is this funny number, e to the r delta t minus d on U minus d. Right, several things to point out. If we look at this number here, e to the r delta t minus d on U minus d, go back to the arbitrage. Go back to the arbitrage. E to the r delta t is certainly greater than d. U is certainly greater than d, so it's certainly a number that's non-negative. Okay, agreed? What about the number on the top? The number on the top is e to the r delta t delta t minus d, the number on the bottom is u minus d. So the number on the top, which is the difference of these two, is less than the number on the bottom, which is the difference of those two. So that number here if that inequality holds, that is a number between 0 and 1. Right? So now let me write something there. What have I got? I've got a number between 0 and 1 times VU plus the 1 minus that number between 0 and 1 times VD. If you'd ask the question, what is this thing in brackets? This is the expected value of V of t plus delta, or of Vt plus delta t, sorry, given that I'm at time t. Okay, and it's an expectation under a funny probability. It is not the real world probability. The share price goes up with real world probability P or down with real world probability 1 minus P. What I've actually got here is I've got an expected value. This is the expected value of the future share price. Why? Well, if it goes up with a probability, Q is a number between 0 and 1, you can think of it as a probability. Any number between 0 and 1, you can think as a probability. So the probability that I end up with VU in this different probability measure is Q times VU, the expected value there. And then when it drops, you've got 1 minus Q, the probability that it goes down. So you add a 1 minus Q times VD, add those two together, and that's the expected value of V of t plus delta t, given that we're at time t. So what we actually can write down here is we have a the value of the option or the replicating portfolio at time t is the discounted from time t plus delta t to t expectation under this funny new probability measure of the future values given f sub t is the filtration, it's the time up until now, the value of the portfolio now. Because you're at this point and you've got to rise up or rise down. And that is the fundamental formula that is going to govern all the valuations of options, both in discrete time and continuous time. Okay? So that will be etched on your brains by certainly Easter time. Right, so the Q here is not a real world probability. It is not the same as P and 1 minus P. Okay? But, because you might disagree with me over what P and 1 minus P is. I might be optimistic about the share price, say it's going to rise. So I'll make P bigger than, say, I'll say P is 0.7. You might be pessimistic about the share price. So you might make P 0.3. We might never agree on what that P value is. But at the end of the day, the replicating portfolio doesn't give two hoots about the real world probability, because it works on this Q probability. This Q probability is called the equivalent martingale probability. Okay? Or, as we'll see in a minute, it's called a risk-neutral probability measure. So the key thing here is we may disagree on P and 1 minus P, but providing we agree on U and D, and we're in the same market so that we use the same value of R, we will agree on what the replicating portfolio is. That's why I've written the clever and confusing bit, read it slowly. Because it is very confusing when you first see it, but it's actually the brilliant thing that allows us to do the valuation. So at the end of the day, we don't care about what P and 1 minus P is, providing we agree on R, D, U and D, which is equivalent to assuming that, both of us assuming that the share price behaves in the same distributional way in the limit as delta t goes to 0. Then we will agree on the risk neutral probability, we will agree on the value of the replicating portfolio at time t. Okay, so what's the point of that? Well, the key step of that is, I'll jump ahead to the end. Let's suppose that this was the expiry time. Let's suppose that t plus delta t was equal to capital T. Okay. Now, if you're valuing a European option, the only thing you know about that European option is the final value of that option. You know that it's either going to be something like, so if it's a euro call, okay, it's going to be max of st minus k and 0. If it's a euro put, it's going to be max of k minus st and 0. That's the only thing for sure that you know about the European call option. You know the value at expiry, at least in terms of what the st is at expiry. Okay? So that's the magic, because if I make this the expiry time, I know what VU and VD is. If I know what VU and VD is, because what I want is, I want to have a portfolio that at expiry, whatever the outcome of the share price, allows me to liquidate the portfolio and pay you if you exercise your option. Okay? So if I set VU final, and of course that means it's known, and VD, known values of the option, then what it does is that tells me the phi and psi that I've got to hold